All right, sorry for the slight delay. Can you all hear me?
Yeah, I can hear you.
You can hear me? Okay, good. All right, I just want to make sure. Just some announcements. The worksheet, the Gauss's law worksheet, did have a mistake on it. The density should have been this. I forgot to put the absolute value signs. And without, if the density is this, or F, I forgot, I think it was an X, sorry. Oh no, it was a Y, sorry. If the density is this, then the field outside the slab here and here would be 0. Okay? And I didn't want it to be 0 outside. So, and when I designed the problem, I designed it for the absolute value sign. So, I neglected to add that. Okay, so that would make the field non-zero outside. So I'm giving you guys an extra day to work on it because of my mistake. I do have student help hours tomorrow, so if you have questions on the worksheet, please ask. So again, this is what the density should look like. So the worksheet's due on the 1st. The multimeter quiz is due on the 3rd, and the other item that's due is on the 6th. And so that's the chapter 25 homework. And then exam 2 is next Friday. And exam 2 covers chapters 23 to chapter 25, nothing else. Next week, I will be starting on chapter 26. Nothing in chapter 26 will be on exam 2. So we're a little bit ahead of the exam date, but that's okay. I mean, you'll have plenty of time then to get the homework done and study for the exam. All right? I know I'm here on campus today, but I'm going to have to leave after this class because I got there's some school things I need to get done. I will be here on Friday because people have asked. I'll be here on Friday to do the labs, but then also from 12:30 to 1:50 I'll be free, and also after 3:30 I will be free. But if most likely I will be here till 4 o'clock on Friday unless I have a bunch of people asking me questions. Okay, so my goal on Friday is to leave by 4. But I do have free time between 12:30 and 1:50. I'll be in between classes. All right, so you can come at that time and ask me any questions you have, either on the worksheet or on the next homework. Okay. So today what we want to do we want to talk about calculating the electric field from our knowledge of the electric potential. We're going to talk about equipotentials. And calculating the electric potential. And the latter will go a little bit faster than we did for electric fields because I think this topic, number one, is going to be a little bit easier for you because you've been exposed to calculating electric fields. The process is very similar, except these are scalars. Okay, so we'll be going a little bit faster than that. And I'm going to show you several methods. And then we'll go fairly quickly over the concept of equipotentials. Any questions before I get started? Okay. So this is a review of the main equations we discussed the other day. We did talk about the potential due to a point charge and the potential energy stored in a system of two charges. So I will leave that up for a little bit. What I want to start with is a discussion on calculating the electric field knowing the electric potential. The process of calculating this is fairly straightforward. I want to start with our definition of how to calculate the electric potential. Delta V is minus the integral of E dot dr. Okay, and if I don't integrate this expression, what I really have is dV is minus E dot dr. And what this represents is the following. That is what this expression represents, okay, right there. Now, if I take a look at, oops, I don't know what happened there. Okay. If I take a look at how, if I said dy and dz to be 0, then I will see that dv is equal to minus e sub x dx. And furthermore, dv over dx, keeping y and z constant, is minus e sub x. I can move this minus sign to the other side, and so e sub x is just the derivative of the function representing the electric potential due to some charge distribution with respect to x, holding y and z constant. And then Calc 3, there's a special symbol for this. It's called a partial derivative. And I can use the same argument for e sub y and e sub z. As a result, E, so this is the x component of the electric field, is minus dv over dx I hat plus a negative dv over dy j hat plus a negative dv over dz k hat. And we can write it like this. And this symbol is called the gradient. And the gradient is written like this. Okay, and then you put the function here. That's what that symbol means. So you can write it either this way or the shorthand way that way. So we can write it also this. Okay. And the gradient is something you learn in Calc 3. It has to do with the path of greatest descent. Okay. You don't have to know all the mathematics behind what the gradient means. You'll learn that in Calc 3. But we're going to just use this as a way to calculate the electric field from our knowledge of V. And it's pretty straightforward. If you're given V, all you got to do is take the derivative with respect to x, the derivative with respect to y, and the derivative of v with respect to z, and you have the x, y, and z components of the electric field. That's it. Okay. Questions on that? It's much easier to calculate E from V as opposed to calculating V from E. So let's do an example. Suppose we're given, suppose you're given V is some function of x, y, and z. Let's see, 2000. So let's say we're given this expression. Ooh, let me check the chat real quick. Okay, so you're asking there are 3 ways to find the electric field. Do you mean in terms of the integral of k dq over r, Gauss's law, and this method? Is that what you're alluding to? Yeah, you're right in that sense. There are 3 ways we can actually determine, but then the given information is different, right? Because this method requires us to know V, whereas the other methods require us to know something about the charge distribution. Okay, it's just that the information that you're given is, to start with, is a little bit different. But yeah, you do have 3 different methods, and you want that. And the reason why you want that is because it might be easier to calculate E using one technique as opposed to another. Same thing, for example, when you're doing, in Physics 205, you're doing a pendulum problem, and you want to calculate the speed of the pendulum when it gets to the bottom. You can use Newton's laws, solve for the acceleration, and then integrate over a time period from t equals 0 to whatever this t is. But that's a very it turns out that it's very difficult to do that integral. However, if you use conservation of energy, you can find V at that point very easily. Okay, so yeah, you do have multiple ways of calculating E. That's a good observation, and it depends on what you're given. Okay. So let's say we're given this charge distribution. Not this charge distribution. This V. And I want to calculate the electric field. All I have to do is use this expression. So I can take the derivative of this expression with respect to x. And that'll give me the x component. So that's going to be minus 3. Oh, there's 2 minuses. I take the derivative with respect to y. There's no y term in here. You don't have to put that in there, but I'm just putting it in there to show you that the y part is 0. And then I take the derivative of this with respect to z, and don't forget the minus sign. And what are the units? I can write it as newtons per coulomb, but look, it's volts per meter. So we can write it also as volts per meter. So an electric field can be written as newton per coulomb or volt per meter. Okay. Questions on that? So this is straightforward. I mean, these calculations are straightforward. I think you have one problem on this. Again, it should go pretty quickly. Let's go back and take a look at this expression. And let me erase everything else. And I want to consider the case when this is 0. Well, obviously, E can be 0. Well, what is another case? Well, this is a dot product. What about the case where the dot product, the angle between these two vectors is 0? So if you move in a direction perpendicular to the electric field, the electric potential doesn't change. The fact that you have an electric field means you have a potential gradient. Okay? The fact that you have an electric field, you have a potential gradient. V changes in space. And so when you put a particle in a region in which V varies, it's going to experience a force, a charged particle, sorry. When you put a charged particle in a region in which V varies, it's going to experience a force because a varying V means you have an electric field. In the same way as if you have a pressure gradient between my two hands, if you put an object between my two hands, the object will experience a force because of its pressure gradient. Right? Pressure gradient, you know, when you have pressure gradient, you have wind, right? So if you move along a path in which E is perpendicular to dr, dV is equal to 0. That means that there's no work required to move a particle along a path in which dV is 0. And for charge distributions, we can find surfaces in which dV is 0. So let me give you an example. Suppose I have a point charge. Let's make it a positive charge. Let me draw the electric field lines. I'm going to draw about 8 of them, okay? If I move in a direction perpendicular to the field lines, I will get a surface in which V is constant. If dV is 0, that means V is constant. So this surface has V equal to be a constant. And that makes sense because what's the electric potential due to a point charge? Well, the electric potential due to a point charge is kq over r. Anywhere around the circle, the distance from the point charge is r, the same value. And so V is the same anywhere along the surface. I know I didn't draw a surface, okay? I drew something two-dimensional, but just think of 3D, okay? This surface at which V is constant is called equipotential surface. And one can do problems to determine determine equipotential surfaces, although they're not easy. We're not going to do those problems. I'm not going to have you calculate the geometry of an equipotential surface for a charge distribution, because that's a hard problem. Although we can draw them based on some of our knowledge. We can estimate what they would look like. Okay, I'll give you a couple of examples. But for a point charge, it's easy. The equipotential surfaces are basically spheres. Let me use a different red color. A different red marker, sorry. Those two red spheres are surfaces of equipotential because r is constant. Remember, V is kq over r. And those surfaces are perpendicular to electric fields. And in fact, if you can draw the equipotential surfaces, you can actually determine the electric field, because the electric field is going to be drawn perpendicular to the surface. Let me give you an example. So in graduate school, I took a course on experimental methods. And so I had a fairly old-time instructor who taught the class. And so he wasn't very familiarized with using computer methods for doing calculations. And so he talked about if you're designing experimental equipment, like for an accelerator, etc., you also have to calculate the electric fields when you're designing the system, because how do you know what the particle is going to do when it goes through various geometries? So he said, suppose we have two conductors like this. How do you calculate the field in between the plates? He said, well, in the old days they didn't have computers that's going to allow them to do the calculation, because because of this geometry, you really need a computer to do the calculation. You can't just integrate something and get get an answer. So you have to actually do a numerical calculation. What they did in the old days is they actually did it experimentally. There's paper that you can buy that's called conductive paper, and you can paint with a special kind of paint, conducting paint, this configuration, this geometry on the paper. And the paper conducts electricity. It has a high resistance. And what you can do with a voltmeter, you take a voltmeter and you put one lead of the voltmeter at a reference point, and the other voltmeter you find, for example, let's say you put 6 volts between these two. Let's say this is 0 volts, this is at 6 volts. Okay, so you put one lead here, you take the other lead and just find the locations where the potential is 1 volt. Find all the location, and you draw a dot. Every dot that you draw represents a location where the meter reads 1 volt. And then you connect them with a line. Then you repeat the process. You put one lead here, and then you measure every place where the voltage is 2 volts. And then you do 5 volts. And so these represent, you've measured all the places where the voltage is the same. The electric field lines then, they go from negative, they go from positive to negative. They go from the higher potential to lower potential. The electric field lines then just look like this. Where's my purple marker? Oh, there we go. They're perpendicular to the equipotential. So that's why this is useful. You can actually map out the fields from your knowledge of the equipotentials. What about let's say we have a conductor. Okay, let's say we have a conductor. What do the equipotentials look like for a conductor? In fact, for a conductor, the equipotentials pretty much take on the shape of the conductor. Why? Let me draw a triangular plate. And let's say it's charged. Let's say it's positively charged. And of course, the charges are going to be bunched over at the corners here. Okay. What do we know about conductors? We know that the electric field inside a conductor is 0. We talked about that the other day. And I did a demonstration for you. We also know that the electric field at the surface of the conductor is perpendicular to the conductor. So right at the surface, E has to be perpendicular. Why is that again? Because if the electric field had a component along the conductor, then any electrons on the surface or any charge on the surface would move along the surface of the conductor, and that means the conductor is not in equilibrium. Well, if there's no component of E along this direction, then anywhere along this direction, V is constant. So the surface of a conductor is an equipotential surface. Okay, the surface of a conductor is an equipotential surface because there's no field in this direction. So if you move along this direction, in fact, you're moving perpendicular to the electric field anyway, V is constant along the surface. So the surface of the conductor is an equipotential surface. And any other equipotential surface that you draw has essentially the same shape, because if this is what the electric field looks like, the equipotentials look like this. And as you get further and further away, these get more round. Okay, et cetera, et cetera, et cetera. And the field lines are perpendicular to these. So you can get an idea of what the field lines will look like for a conducting surface that's charged. Okay. So because of this surface is an equipotential. And there's no component of E in that direction also, so we can argue both ways. So let's sketch an equipotential surface in electric field lines for a uniformly charged conducting plate. In fact, I'm going to do 2 plates. I'm going to do 2 plates that are perpendicular to each other and they're grounded. The conducting plate is this one. Let's do 2 conducting plates with an electric charge in front of it. Sorry, I misspoke a minute ago. So let me have 2 perpendicular conducting surfaces, and they're grounded. And we put a charge, Q, over here. And of course, let's say it's positively charged. What's going to happen? It's going to, from ground, you're going to get a whole bunch of negative charges over here. Remember, the surface of a conductor is going to be an equipotential. And so all the equipotentials are essentially going to take the shape of the conducting surface. And as you get further and further away, these get more rounded. So the red's the equipotentials. The electric field lines, then I would draw perpendicular to these equipotentials. I'm drawing these right angles there so that you know, even though the drawing might not be nice, so you know that they're perpendicular. Okay, so that's what the field lines would look like. And in fact, this is a problem that can be solved in a physics class, but usually this is covered in a graduate course. That's actually not an easy problem. Or actually, sometimes in a junior level course, it depends. Okay. But the only thing we can do is just draw the equipotential lines and the electric field lines. At least we'll have an idea of what the field will look like. And over here, and beyond. Okay. We get a conceptual understanding using our knowledge of equipotentials, even though we're not able to really solve that problem, at least here. Okay, so now what I want to do is I want to show you how we calculate electrical potentials for various types of charge distributions, either the discrete charge distribution or the continuous charge distribution. We're going to start doing the discrete one. And really, the other day I talked to you about how you calculate it, because the other day I said, well, if we have a point charge, this is V for a point charge. And if I have a bunch of them, since this is a scalar, all I just got to do is find the value of V for each one of them and then add them up. In other words, and I'm going to rewrite something I wrote the other day. If I have a charge here, charge here, and this is some point P. Then V is just K Q1 over R1 plus K Q2 over R2 plus K Q3 over R3. That's it. If I have n of them, then V is equal to the sum of K Q sub I over R sub I from I equals 1 to n. Okay, so it's pretty straightforward. Let's start with a simple one. And I do want to calculate the electric field. And I did notice that this problem has a subtlety in it that I actually forgot about. But anyway, I'll bring that up. All right. So I have two charges. Let me draw my coordinate system. I have one charge at the origin, negative q, positive q. This distance is a, this location is x equals minus a. This is point P. Some arbitrary distance y from the x-axis. I want to calculate the electric potential at that point due to these two charges. Okay, so all I got to do is find the electric potential due to this one. This is a negative charge. And then the electric potential due to this charge at this point. Well, the distance from here to here, in order for me to get the distance between these 2 points, I have to use the Pythagorean theorem. The square root of this squared plus that squared. And so that's going to give me and I'm done. However, if I want to find the electric field from this expression, the first thing I need to do is write this in general as a function of x and y. Then I got to find the gradient of that expression. Okay? So then I take the gradient. And the subtlety there's a subtlety that comes in because of the fact that this vector r is the magnitude of a vector that goes from here to here. And you have to write it carefully, otherwise you're going to make a minus sign error. And so what I'm going to do is to alleviate that issue, I'm going to treat this just as a distance, okay, instead of a coordinate. When you take a junior level course, you will see where this subtlety comes in. All right, so I'm going to take the gradient of that function. What do I get? Or minus the gradient. Well, if I take minus the gradient of this, I'm going to get, oops. Right, I'm going to get that expression. And then I got to take the, oops, sorry. Let's do the derivative with respect to x first. Okay, I wrote it in general. I said something and I didn't write it down. So let's take the derivative of this with respect to x, minus the derivative of this with respect to x. This is not going to do anything. So when I take the derivative with respect to x, I'm going to get k, qx okay. Questions on that term? Then I take the derivative with respect to y minus the derivative with respect to y. What am I going to get? Oops, I forgot a minus sign here. Everyone okay with that when I take the minus the gradient? And if I did it too fast, you can try it later. This is the correct expression. And then I'm going to treat, because of the subtlety that I want to treat this as a distance, not as a coordinate. And so I'm going to plug in x equals a. And then I'll get the expression for the electric field at that point. Of course, you can also get the electric field another way, right? And that was the question you had asked. You had asked Aaron, there's another way of calculating electric field for this. We learned that in chapter 23. Okay, so we have more than one way to calculate electric field, but here we had to find V first. So it's a little bit more work. Okay. Questions on that? Concerns? You have a bunch of problems in the homework where you're dealing with discrete charge distributions. You're calculating V, you're calculating how much work is required to move a charge between two different points based on some charge configuration that's in that region, or in the region of the charge, sorry. You're going to calculate E from V. So there's a lot of problems where you're going to be doing these kind of calculations. And really, I only need to do one example on this topic. What I want to do now is talk about calculating the electric potential due to a finite charge distribution. I'm sorry, a continuous charge distribution. Meaning I can't count the number of particles that make up the system is not countable. Okay. So there's really two methods I can use to do this calculation. And I'm going to show you both. So let me start with a simpler case. Suppose I have some charge distribution, whatever it is. I want to calculate V at that point. In order for me to be able to do this, I have to break this up into pieces small enough so that V is constant. V at this point is constant over that piece. And I got to do it for all the pieces that make up this object. So I'm going to use this as a dq. So this is going to be a point particle with charge dq. And this is going to be the distance r between dq and p. And so then what I'm doing is calculating really a dv due to this point charge, because this is part of the potential at this point. This is a small piece that contributes to the total potential at this point. I'm going to call it a dv. And then to find the total potential, I got to sum up over this dq, all the dq's that make up this object, which means I have to integrate this. This assumes then that I can break this up into a bunch of point charges. that my total charge that I have of the system is finite. And that V is 0 to infinity, because when I derived this equation the other day, I assumed, or I made the assumption that V was 0 to infinity. If I have an infinite line of charge, the total charge on this thing is infinite. So I will not be able to use this expression to calculate the electric potential due to a line of charge. I have to use a different method. Well, the other method is basically going back to the definition of what delta V is. If we can calculate delta V and we know the potential at some point in space, we can get V. Okay? So, this method that I'm going to talk about first assumes a finite charge distribution. Okay? And it comes from us knowing the field, the electric potential due to a point charge. So all we got to do is find an expression for dq and an expression for r. And that's it. It's a scalar. We don't have to worry about r hat or anything. So these are actually, to me, easier to calculate. So when we look at the method that we would use to do these calculations, there's one step missing here because of the fact that we don't have to figure out r hat. So you choose a coordinate system, write your expression for dq, determine r, and then integrate. And check your answer and make sure it's correct. Okay. And again, this method is only valid for a finite charge distribution. Since V equals 0 as r goes to infinity. So I want to just do two examples. And these should go fairly quickly. I want to calculate the electric potential as a function of G for a disk. Really, I want to do it along the axis of the disk. So I'm going to erase all this just so I can get more board space. So I want to find the electric potential along the axis of a disk, a solid disk. Let me try to draw this. So there's my disk. It's a solid disk. First question is, how do I break up the disk? I want to find my dq. In other words, I want to break the disk up into a piece small enough such that V is the same over the entire element. And it turns out for a disk, I can break this up into a bunch of rings. You know, like when you look at an old tree. Old tree has tree rings. So the red that you see here on the board is a ring of charge of thickness dr and circumference 2 pi r. So this radius is r. The radius of the disk itself is a. So let me draw the radius of the disk itself. I don't know if you can see that. Maybe I made it too small. I apologize. And so if I were able to take a pair of scissors and cut this ring out, this little ring out, and make it and stretch it out, or not stretch it out, but make it straight, then its length would be 2 pi r, its thickness would be dr, and its area is this times this. So dA is 2 pi r dr. That's the element of area. And so our dq is the charge per unit area times dA. And if I integrate over all the radii, then I get the total charge of the disk, which is Q. But this disk is uniformly charged, so the charge per unit area is simple to calculate, just Q over the area. So what does that leave me with? That's my dq. You've kind of done problems like this before. I think you got to go back to chapter 23, problem 9. Okay, that's why I assigned that problem, because you need to go back and understand that problem so you can figure out your dq's. Now, what is the distance from point P? And let me draw it in black. To the ring. That's supposed to be a straight line. Well, is this going to be Z? And that's going to be R. So I'm going to call this, the distance capital R is going to be the square root of Z squared plus R squared. I have everything I need now to write my expression for dq. dq, I'm sorry, not dq, dv is k times my dq over that. To find the total V at this point due to all the rings that make up this disk, then I integrate over all radii. And let me pull out some constants. Actually, let me pull out some constants and make it a little bit easier. So you can see the integral. Okay, I'm not going to spend time doing the integral. You can use a technique to solve it, like U sub. Okay. I'm just going to eventually, in a second here, I'm just going to show you the answer. Your math instructor that I actually didn't go through the process of integrating this. Okay, so that's what I'm integrating is that expression. So what do you get when you actually perform the integration? You get that. And so V ends up being 2kq over a squared times the square root of z squared plus a squared minus the absolute value of z. Because these quantities have to be positive. Now, one thing we can talk about is the electric field. We know that the electric field, we know that we can calculate the electric field along the axis. We know that the y and z components of the electric field are going to be 0. I'm not even going to take the gradient of v with respect to, I'm sorry, the x and y. The components of the x and y component of the electric field are going to be 0. Only the component of E in the z direction is not 0. So when I take the gradient of this, all I need to do is take the gradient of this, really the z component of the gradient. I just need to take dv dz, and I have the electric field. Because I know the x and y components of the electric field are going to be 0. Okay. To do that, though, I mean, I don't have to put in anything in terms of x and y here. All right. And if you actually calculate the electric field, you should get the same result as what I got in the video where I calculated the electric field from the integral of k dq over r squared. Now this plate has symmetry so that the charge distribution has to have the same form above the axis as below the axis. Okay? Whether you're above the axis or below the axis, because the charge distribution is symmetric about the plane, V has to have the same mathematical form. And sign, I mean, the same sign. It's completely symmetric. The V is going to be reflective of the symmetry of your charge distribution. What if z goes to infinity? What if you're really far away? What if you're very, very far away from the disk? What should the electric potential look like? Well, it should look like that of a point charge. You should get you should get kq over z. And of course, if you do an expand, I'm not going to do that here because we've done something like this before. If you do an expansion of this when z is much, much greater than a, you will get that expression. Okay? You will get that expression. What if A goes to infinity while keeping the same charge density? If you keep the same charge density and A goes to infinity, then the total charge becomes infinite. And then this method that I use to calculate the electrical potential is not valid. Okay. We can also talk about what does the electric potential looks like very close to the disk. And of course, then we have to look at how we expand this function. What if sigma is not uniform? If sigma is not uniform, then this term would be inside the integral and it would be part of the integral. And you've seen that in other problems. Let me show you a graph of what V looks like. I'm gonna blow this up. Just give me a second here. If you plot V as a function of Z on both sides of the disk, that's what the charge distribution looks like. That's the plot of that function. And the electric field looks like that. Now, what do you notice? Well, first of all, the electric potential is continuous across that surface. That has to be true. So the function for the electric potential has to be continuous across a boundary. Why? Well, because if E is the gradient of V, if E is the gradient of V, you got to be able to take the derivative of V. I mean, V has to be continuous. If V is not continuous over a boundary, then the electric field is infinite. You get something that's non-physical. Okay? If V is not continuous over a boundary, the electric field is not a physical thing. You'd have an infinite electric field. However, the electric field can be discontinuous across the surface, and that's what you see in the second graph. The fact that you have a discontinuous electric field across a boundary just is reflective of the fact that you have a surface charge density. Okay, you just have a charge on the surface. So you can have a discontinuous electric field. You cannot have a discontinuous electric potential, because otherwise that would result in a non-physical electric field. Those are two important things to remember, because they're going to come up later in our discussion. Okay, I want to do one more problem. And this should be a familiar problem, because we calculated the electric field for this system, and here we're going to calculate the electric potential. We can take the expression for electric potential and differentiate it to get the electric field. So let me draw my system. I'm going to define my coordinate system. Here's my origin. The left end of the rod is at the origin. Okay, I made the rod kind of thick, just for emphasis. Let me know if you can't see the green. Can you see that okay?
That's kind of hard to see it.
Hard to see? Okay, I won't use green. Okay, I thought maybe I can get away with using green, but I cannot. All right. So I will keep using dark colors. The length of the rod is L. We want to determine the electric potential at point P. Which is a distance A from the end of the rod. First thing I'm going to do is write my expression for dq. Well, let me write my dq here. Here's a dq. And this dq is a distance of x from the axis. And so I'm going to write my dq, and then I'm going to write my r. Actually, writing the expression for r should be easy. Okay, something's weird with my PowerPoint. So my r will be easy. Let's just do the dq. dq is lambda naught x dx. That's it. Okay. This piece is a length dx. The charge per unit length times dx gives me my dq. But if the total charge on this rod is q, I can figure out what this lambda naught is, because if I integrate over the whole length of the rod, this expression, that has to be equal to q, my total charge. And so if I integrate this thing, I'm going to get lambda naught L squared over 2, and that means that lambda naught is 2q over L squared. And so I can put here 2q over L squared x dx. Of course, if I integrate this over the whole rod, I get q. That's what I should get. What's my r, the distance from this guy to this guy? Well, it's going to be this total distance, L plus a, minus this distance, x. So then my dq is, I'm sorry, I keep saying dq. My dv, I had very little sleep last night. I apologize. I keep making these slip-ups. K times this dq over r. And so v then is going to be the integral from 0 to L, the length of the rod, times, and let me pull out again, let me pull out some terms. So that's my v, and then I'm not going to bore you with the integration details, okay? And let me write down the expression that you get when you perform the integration. So I'm just going to give you the answer. That's v. If I wanted to calculate the electric field, I would write this in general, where this is an x. Take minus the gradient, well, minus the derivative with respect to x, and then plug in back a. And I have my electric field. You should get the same expression that we got in chapter 23 when we did the problem. Let's look at your PowerPoint notes. And you should try that to practice, so you see you understand these ideas. Okay? Questions on this? Okay. So I've given you two examples of how you calculate V for a finite charge distribution. Now I'm going to show you another way to calculate V, whether you have and it works whether you have a finite charge distribution or not. And this is going to go back to our definition of V. I'm going to go back to our definition of, I'm sorry, not V, but delta V. So delta V we define as minus the integral of E dot dr. What this means is if I integrate from A to B, it's V sub B minus V sub A If I know the potential at A and I know the electric field, I can solve for V as a function of R. So I can make point B any generic location. If I know the potential at my initial point, or it really doesn't matter how I do the limits of integration, but let's say this is the initial point, this is the final point. Let's say the final point is some arbitrary R. If I know the potential at A and I know the electric field, I can figure out the potential at any point in space. So whether I have a point charge or any kind of charge distribution, as long as I know the electric field and I know the potential at some point, I can solve for V at some location in space just by using this equation. I forgot the minus sign. This is more general, and it is useful when we know E. Okay. We have to use this when the charge distribution is not finite in extent. Of course, we did use this equation to derive the expression for the potential of a point charge. So even the potential for a point charge comes from this expression. Okay. This is more general. It's based on how we define our delta V. And it's really reflective of the work done on a charge by a field and moving it from one point to another. If that integral is 0, that means that V doesn't change. The V between the 2 points is the same. You have an equal potential. Okay, you have 2 points that are equal potentials. Okay. But if I want to know V at a specific point in space, I need to have V at a particular reference point. Okay, for me to do this problem, it's going to take me more than 10 minutes. Although I would love to do this problem. I cannot. So I'm going to save it until Monday. Yeah, I think I'll save it till Monday. So I'll wait until then. So you should be able to do most of the homework problems right now in the chapter. The only problems that you cannot do right now are problems where you have to calculate the electric potential due to cylinders, anything that's infinite in extent, because I'm going to do an example. Or doing the last, right now that you can't do the last problem on the homework assignment. It's the one with 2 concentric spherical shells. That one you cannot do yet. But you can do everything else. So you should try, and I know this is keeping you busy, you can try to do over the weekend as many of the chapter 25 homework problems as you can. Okay? I need you to do as many of the problems as you can on chapter 25. And then you'll be only left with maybe 2 or 3 problems for Wednesday. I don't want you to spend a lot of time. I want you to try to get this homework assignment done quickly so then you can just focus on studying for this exam over several days. So really I only have a couple more things to talk about. Need to do an example with this, and then I need to talk about electric potentials due to a conductor, or in a conductor, although I've kind of alluded to that today. Okay, and there's one more problem I would like to do that's to me, is very important in helping you to understand the material in chapter 26. Okay, so it's an application. So about half the class on Monday will involve me finishing the chapter, and then the other half I'll start chapter 26. Questions? You folks doing okay? You guys are very quiet today.
Yeah, pretty good.
Okay, doing okay? All right. So hopefully I'll see you you folks, some of you folks in office, student help hours tomorrow, okay, at 5:30. All right, we'll see you then. We'll see you
Thank you,
Thursday,
Professor.
Friday.
Take it easy.
All right.